Dear friends, today we are going to see MCQ 1 regarding the paper algebra. So the first one is if A is equal to matrix 1 1 and B is equal to 1 0 minus 1 0 out of this four option. So we know that this matrix is a non-zero matrix, not equal to 0, and these two non-zero matrix. And just multiply this one 1 1 and 1 0 minus 1 0, which you can see here 1 minus 1 0, again 0 0 0. So A not equal to 0 and matrix B not equal to 0 and AB is equal to 0 matrix. This is the condition for zero divisors. So the option is zero divisor. The next question is the following statement is false. So every field is an integral domain, every field is a ring, every ring is a group or all true statement, and the statement every integral domain is a field is a wrong statement. So according to this question, this is the correct option. So remember every field is an integral domain. But integral domain is not a field. And the third question, a field is defined as a field is defined as a finite integral domain. So remember this one. A field implies integral domain, but integral domain need not be field. But finite integral domain implies field. So that is here. A field is defined as finite integral domain. So remember these conditions. And now we can see the fourth one. A field is a commutative division ring. So here an option is there, integral domain. If this option is finite integral domain, then it may be correct. So if not, then the option is commutative division tree. And so here we can include that the field is a commutative division array. Now we can see the fifth question. Fifth one, F is a field and F is an integral domain. Out of this four option, you can understand that field implies integral domain and the integral domain does not imply field. So option 1 is right. But if it is finite integral domain, then definitely it implies field. Now the sixth question, sixth one, a commutative division ring is a finite integral domain, because before itself we see commutative division ring is a field, and from this both we can say that commutative division ring is a finite integral domain. Now we can see the seventh one. If R is a commutative ring with unit element and M is a maximal ideal if and only if R by M is a field. So the question may be, sometimes if R is a commutative ring with unit element and R by M is a field, then M is a maximal ideal. Then you can see the eighth one. If F is a field, then its only ideals are 0 and F itself. So this two is true. If it is a field, then F and 0 itself are the only ideals. Then the ninth question. If R is a commutative ring with unit element, then the only ideals are 0 and R itself. If it's so, it is a R is a finite integral domain. The above one we see F is a field. F is a field, then its ideals are F and 0 itself. In this question, R is a commutative ring with unit element, then the only ideals are 0 and R. If it's so, R is a finite integral domain. And the 10th one, every integral domain is not a field. So we see here field problems, that is field implies integral domain, but integral domain does not implies field, but finite integral domain implies field. So we can say that every field is a field is defined as finite integral domain. And not only that, every field is a commutative division ring. So we can say that commutative division ring is finite integral domain. And again, we see that if R is a commutative ring with unit element and the only ideals are 0 and R itself, if it's so, R is a finite integral domain.